So we're going to talk more about variation and standard deviation and mostly about what they mean and how they can help us learn about the data. So the first thing we're going to do is really just look at graphs and see if we can interpret the standard deviation from the graph and estimate it just to get an idea of what's happening. So when we interpret the standard deviation, we want to remember that it is a measure of the typical amount an entry deviates from the mean, right? So we're looking at how far away are the other values, are the entries, so the other data points from the mean or the center, right? So the more entries are spread out, the greater the standard deviation is. So if you have a high standard deviation, that means your data is more spread out. If your standard deviation is close to 0, that means your data is more clustered close together, right around the mean. So that standard deviation tells you how spread out your data is. And just as a side note here, I thought this was a good study tip, which is why I left it in. You can use standard deviation to compare variation in data sets that use the same units of measure and have means that are about the same. So that's when it's most helpful. So for instance, in the data sets over here, right, where the mean equals 5 is shown. So if you look at each of these graphs here, the mean is 5 in each case. The data set where the standard deviation is about 3, which is here, is more spread out than the other data sets. Not all data sets, however, use the same units of measure or have approximately equal means. So we do have another method we'll use later on at the end of this section called the coefficient of variation to compare those sets. But if you have data that has the same mean or very similar mean, like close together, then you can use the standard deviation to compare them to see how spread out they are. So notice here, each of these, so don't look at this part yet. Each of these graphs has the same mean, right? They're all 5, and we can see the data. So in this one, the standard deviation is 0 because every single data point is the same as the mean. So there's no variation at all. Every single data point is 5. That's it. So no variation, which is why your standard deviation is 0. Here is another data set. So you have one data point that was a 3, 2 that were 4, 4 that were 5, 2 that were 6, and 1 that were 7. We can see a nice symmetric and bell-shaped graph here. Again, our mean is still the 5, and you can see the standard deviation is pretty small. It's 1.2, and that's because our data is pretty close together, right? It's all kind of clustered around that center pretty symmetrically. And in this last case, our mean is 5, so our center of our data is right here at 5 in the middle, but our data points are pretty spread out. We don't actually have any data points close to the mean. They're all kind of far away. So we have one data point at 3 and one at 7, and then we have 3 data points at 2 and 3 data points at 8. So our data here is much more spread out compared to the other sets, and so you see a larger standard deviation. Let's do one more example, similar. So without calculating, actually we'll scroll down so you guys can see the top a little bit, estimate the population standard deviation of each data set. So again, we're just estimating here. We're not actually going to calculate. But here's our first data set. So they're telling us that the mean is 4. So here's our mean right here. And I have 8 data points, which makes sense because my height here is 8. So all 8 of my data points are also 4. So every data point is the same. They're all 4, and they're equal to the mean. So when that's the case, your standard deviation is going to be 0. Now, I'm using the Greek lowercase s instead because we're talking about population. So that's why we're using mu here instead of x bar. So these were graphs of samples. So we're using x bar and s for standard deviation. These are graphs of population data. So we're using mu and that lowercase sigma here. All right, let's look at the next one. So here we're told that our mean is 4 again. So our mean is right here, right in the center of our data. Again, we have 8 data points, which makes sense. I have 4 data points that are 3 and 4 data points that are 5. So for instance, my data points are 1, 2, 3, 4, 1, 2, 3, 4. So those are my data points here. And we're trying to estimate the standard deviation. So we're looking at how far apart are these data values from the mean. Well, the mean is 4. Either our data is one value higher than the mean, or our data point is one value less than the mean. And it's pretty much the same in both directions, right? It's pretty evenly or pretty symmetric here. Not bell-shaped, but it is symmetric on both sides of the mean. So I'm seeing a +1 or -1 change. So I'm going to estimate my standard deviation here is, 1. So again, from our mean of 4, all of our data points are either 1 above or 1 below. So approximately our standard deviation is going to be around 1 here. Now our last set, we have the same mean. So still 8 data points, right? So you have 2 data points at 1, 2 data points at 3, 2 at 5, and 2 at 7. So our data points are 1, 1, 3, 3, 5, 5, 7, 7. You don't really need to write them out, but just in case you're having a hard time seeing that. And I want you to look here. Our data is more spread out than this one, right? So it's much more spread out. It's getting wider. So I have some data points that are +1 or -1 from the mean, but then I have my 7 and my 1. So that's +3 and -3 from the mean. Just kind of think about an average here. So your standard deviation is an average, kind of average. I kind of could average this as a change of about 2 ±2, right? So if I add 3 plus 1 and divide by 2, I get 4 divided by 2, which is 2. And then if I do the same thing over here, I get -2. So it's like on average, I either have a +2 or -2 change. So I'm going to estimate my standard deviation here is about 2. Now, if you actually calculate this out, you can do it using the formula or in a calculator. You actually see the standard deviation is 2.2. So our value is not exact, but again, it just gives us an estimation, and hopefully you can start to see, the higher your standard deviation, the more spread out your data is. The smaller your standard deviation, the closer your data is to that center or that mean. Now, data entries that lie more than 2 standard deviations from the mean are considered unusual. This is a really important idea. So we're going to come back to this idea throughout the course. But if a data entry is more than 2 standard deviations away from the mean, then we say that that is quite unusual. Um, and if they lie more than 3 standard deviations from the mean, they are very unusual. So data that is close to the mean is more normal, more usual, and data that gets really far away, kind of like that idea of an outlier, so similar idea, it becomes more unusual to see that. Unusual and very unusual entries have greater influence on the standard deviation than entries that are closer to the mean because the standard deviations are squared. So remember that to calculate standard deviation, we square everything. So these values that are really far away from the mean tend to really, again, pull that standard deviation, just like they pull the mean in the calculation as well. So they have a lot of influence. Now, many real-life data sets have distributions that are approximately symmetric and particularly bell-shaped. So they look like this kind of like right here, this bell shape. We call that a bell shape, almost like an upside down U. And there's actually a lot of data that naturally follows that pattern. So for instance, heights and weights, if you have a large enough sample size, naturally follow that bell shape on their own. So we actually have a lot of data that is naturally bell-shaped, not everything, but there's a lot that is. And like they say here, the distribution of men's and women's heights in the US is one example. So they're approximately symmetric and bell-shaped. And you can see the examples here. So this is actually the data, and they're showing you that you get about this, bell-shaped curve when we graph it. Now, when we have bell-shaped data, we have something called the empirical rule that is extremely helpful and tells us more about how to interpret standard deviations. But this is only true for bell-shaped data. Okay. And here's a picture of the bell shape with the empirical rule as part of it. So let's read through this. It says, for data sets with distributions that are approximately symmetric and bell-shaped, the standard deviation has these characteristics. About 68% of the data lie within one standard deviation of the mean. So what you're seeing here, I know it's hard to see, this is your mean right here in the center. This is your mean plus the standard deviation. This is your mean plus 2 standard deviations. And this last one is your mean plus 3 standard deviations. And it's the same thing on the other side. This is your mean minus 1 standard deviation. This is your mean minus 2 standard deviations. And this is your mean minus 3 standard deviations. And what we're saying is that when you're bell-shaped, most of your data is huddled around the mean. So about 68% of your data is from here to here, meaning that it is within 1 standard deviation of the mean, plus or minus. 95% of your data is within 2 standard deviations of the mean. So plus 2 standard deviation or minus 2 standard deviation. So this is that same idea that anything beyond this becomes unusual, right? 95% of our data here is within that 2 standard deviation mark. So if you're beyond that, then it starts to become unusual. And then almost the whole thing, 99.7% of our data is within 3 standard deviations of the mean. So let's do some examples here to kind of see what this looks like to make it a little bit more concrete. In a survey conducted by the National Center for Health Statistics, a sample mean height of women in the United States for ages 20 to 29 was 64.2 inches. With the, sorry, I think that should say sample standard deviation of 2.9 inches. So I'm talking about women's height here. I know that the mean is 64.2 inches. And I know the standard deviation is 2.9 inches. And I'm told this is a sample, which is why I'm using X bar and S for my notation. Estimate the percent of women whose heights are between 58.4 and 64.2 inches. Now, we did say, remember that height is bell-shaped, which is key. So because it's bell-shaped, then I can use this empirical rule here. So I'm going to draw my own picture. So my mean here is 64.2. So that's the center of my data. And I want to do my calculations. So I'm going to do the mean plus 1 standard deviation, the mean plus 2 standard deviations, make my graph a little bigger here, and the mean plus 3 standard deviations. And I'm going to do the same thing over here. I'm going to do the mean minus 1 standard deviation, minus 2 standard deviations, and then minus 3 standard deviations. So you can see what we're talking about. And you're using your actual data. So this value right here is 64.2 plus 2.9. So 67.1. This value here is 64.2 plus, now I need 2 of those, so 2.9 plus 2.9, or you can multiply it by 2, right? So I have 18, 19, 20, 4, 5, 6, 7, 8, 9, 10, carry the 1, and I get 70 inches. And then I do the same thing for the next one, adding in the standard deviation 3 times. So 64.2, and again, you can do it one at a time if you want, or you can multiply this by 3, obviously. And we're going to get 72.9 here. And I'm going to do the same thing going the other way. So I'm going to take that 64.2 and I'm going to minus 2.9. And of course, you can use your calculator here. And then I'm going to take that 64.2 and I'm going to minus now 2 of those, right? So I'm going to actually multiply this out. I'm minus 5.8 here. I get 58.4. And then for the last one here, I'm going to take that 64.2 and I'm going to minus 3 of these. And I have 55.5. These are all in inches. So what this tells me is that from about here to here, this is about 68% of the data. So about 68% of my data falls from 61.3 to 67.1 inches for heights. Now, the next set goes from here to here. So it's this whole region, and that gives me about 95% of my data. So 95% of the data in the population falls between 58.4 and 70. Let me see, 0 inches. And let's do another color here. All right, and then my last data right here. So it's kind of hard to color now, but it's the whole thing. That is the 99.7%. So 99.7% go from, let's see, 55.5 inches to 72.9 inches. So basically most women in the United States between 2029, like the vast, vast majority, almost 100%, are somewhere in height between 55.5 inches and 72.9 inches. So that contains a majority of people. Even 95% tends to be a cutoff for a lot of things for what is usual, like I said. So most people for women in this age group are between 58.4 to 70.0 inches. And then beyond that starts to become unusual, right? If you're taller than 70 inches or shorter than 58.4 inches, that becomes a bit unusual. If you're outside these ranges, then that becomes very unusual. So very, very few women are shorter than 55.5 inches and taller than 72.9 inches. Now, I haven't actually answered the question yet. I'm just kind of showing you how that empirical rule works. It's one that we're going to really come back to a lot, this idea that 2 standard deviations tends to be that cutoff for what becomes unusual versus usual, I guess, right? Normal versus not as normal, usual versus unusual. I kind of hate to use those words because it makes you sound like, you're bad if you're in the unusual category. That's not what we mean here. It just means that data-wise, most of your data falls between these points here. And if it falls beyond that, that is an unusual data point. So maybe it's a poor choice of words, the way we say usual versus unusual. We use words like normal, but we're talking about statistics and data specifically, not necessarily, people or things like that. So like I said, I'm just going to apologize for using those terms. Those are the terms we use in stats, although perhaps they're not the best ones and we should be updating this now. But here's our values. So we want to find the percent of women whose heights are between 58.4 and 64.2 inches. So if I look here, I do see some of those values, but they don't quite match my ranges, right? If I said 58.4 and 70 inches, then I know the answer is 95%, right? Or if I said, what were the values between 55.5 and 72.9 inches, I know my answer is 99.7%. So if I had these values, then I have my percents right away, my 68, my 95, and my 99. I don't have those though, so I have a little bit of work to do. And I do think I need some new colors here. Okay, so I'm going to try using yellow. Hopefully we can see it. And I'm going to scroll up for a second. Now, your empirical rule actually breaks down more deeply. So notice that when we say 68%, it's actually not exactly 68%, it's a little bit more. So it's 34.13 plus 34.13. So when you combine these two regions together, you're actually getting what? 68.26%. So it's a little bit more. So again, when we use these values, we're approximating. So if I look at my values down here for my example, I'm going from 58.4, so right here, to 64.2 right here. So I'm looking at this whole region, right, to answer that question. Now, for a rough estimate, if I look at double that, right, I'm at the 95% mark, right? This was my 95% mark right here. So I'm half of that. So half of 95% is about 47.5%. So that's a really good estimate here for the amount of data in this group, right? Because if I double that, I'm at 95%. But again, 95 is an estimate too. So if I just scroll up here a little bit, I can get more exact breakdowns. So I can see this piece right here is 34.13%. And then this piece next to it is 13. 0.59%. So if I add those two together, I get 47.72%. So that's the exact answer to this problem. Estimate the percent of women whose heights are between these two values is 47.72. Again, my rough estimate was about 47.5, just using the rough percentages. So we can see that looks very good. But how did I do that? This is a tough concept for students. So how did I do that? What I did first is I drew a picture. I put the mean in based on my data, and I knew what my standard deviations were. So I actually put all the values in. Before I even looked at the question, I was like, okay, I know I'm using empirical rule here. I know I have a bell-shaped curve. I have my mean, I have my standard deviation. Let's find all these cutoff points. So I found my center. I found my +1 standard deviation. I found my +2, my +3 values. I found my -1, my -2, and my -3 standard deviation values. So I had my main values here. When you have questions about empirical rule, you got to be working off these main values, right? Because that's really what we know. So once I had my main values, I went back to my question and then looked, okay, well, what am I looking for here? I'm looking for 58.4 to 64.2. So that's this region. That's the only piece that I want. So if I go back to my original chart, I see that this little region here was worth 13.59%. This region is worth 34.13%. So I was able to add those together. And we can answer any sort of questions like that based on these cutoffs, right? So if I want the area from, like I said, 58.4 all the way to 70, well, I already know that that's 95%, right? So I have that 95% region. If I want 61.3 to 67.1, I know that this here is 68%. So we're using those main cutoffs to help us break down and find different percents of the population.